Okay, so in this video, we're going to talk about right triangle trigonometry. So essentially this main focus, or the main focus of this video is going to talk about how to use trig functions or trig ratios in a right triangle. So as the objectives say, we're going to look at the 6 trigonometric ratios, and then we're going to apply them to right triangles, like different types of examples. So let's get started. First of all, when we look at the 6 trigonometric ratios, we want to acknowledge what those 6 essentially stand for. So if you see right here, I brought down a whole list of 6 different terms here. And so we're all familiar with the long way of writing it, like, sine, cosine, tangent, cosecant, secant, and cotangent. But in trigonometry, we prefer if you wrote it in their shorthanded form. So sine would be sin, cos is the cosine, tan is tangent, CSC is cosecant, SEC is secant, and then cot is COT, cotangent. Now, you're probably wondering, how does this relate to the right triangle shown above? Well, for starters, if we're looking at trigonometric ratios, we're looking at angles. So first, let's acknowledge that there is an imaginary angle theta right here. So this symbol here represents theta. Now, in relation to the right triangle is composed of 3 sides. And so the most obvious one here is what we call the hypotenuse. The reason it's the most obvious one is because the hypotenuse is the longest side. And we're going to shorthand that and call it hyp. Alright. Now, the side next to the right angle, or that's actually to be more specific, the side opposite of theta right here is going to be the opposite side, as I mentioned. So opposite, or we can also say op. And as you're watching this video, you're going to notice that I'm going to use hyp, op, and the third one, which is adjacent, in their shorthanded form. And just to clarify here, adjacent means next to the angle. So A, D, J. And now let's actually apply it into the ratio. So the following ratios exist for all 6 trig ratios in a right triangle given the angle theta in that position. So here, it would be sine. I know you guys would be tempted to say sin. Sine of theta, as I'm writing it, is equal to opposite over hypotenuse. The cosine of theta, or it's cos, like you guys say it, cos, it would be adjacent over hypotenuse. Then you also have the tangent, opposite over adjacent. Then likewise, for here, you have cosecant, the CSC. Cosecant theta is equal to hypotenuse over opposite. Secant theta equals hypotenuse over adjacent. And cotangent theta is equal to adjacent over hypotenuse. Oops, that should be a P right there. Alright. Now let's actually apply these 6 trig ratios into our next problem. So here we have a right triangle that's been filled out for us. We have a 6, 8, and 10 triangle. Theta is present, the right angle is present. So we can use our 6 trigonometric ratios to find what those values are in this triangle. So let's get started here. So, and just for the sake of the video, I'll go ahead and write out their formulas again. So sine theta is opposite over hypotenuse. And if we look at the values here, opposite over hypotenuse would be 6 over 10. Now, if you are visual like I am, I would probably label these sides as well too. So I'd call this the opposite. I'd call this adjacent. Oops, let me fix that. And then I'd call this one hypotenuse. And that way when you're writing the values, it'll be much easier for you to look at. Like I said, math is really big on being visual, so you want to make sure you are looking at these, with whatever tactics you guys use for making the problem easier. So 6 over 10 is 3 over 5 here. And then cosine of theta, which is adjacent over hypotenuse, that is 8 over 10, or 4/5. So when you're writing your 6 trig ratios, make sure you write them in reduced form. Tangent of theta is equal to opposite over adjacent, which is 6 over 8, or 3/4. All right. Now, before I give you the other 3 trig ratios, let me just show you that there is a trick for remembering sine, cosine, tangent, and I'm going to show you the trick for remembering the other 3. But first, you have this right here. SOHCAHTOA. So SOHCAHTOA represents the 3 primary trig functions right here that are given to us, okay? And so in those 3 primary trig functions, you're going to acknowledge that SOHCAHTOA, so is the sine, the opposite, and the hypotenuse. I'm just writing it vertically because it makes more sense. The cosine is the adjacent and the hypotenuse, and tangent is opposite over adjacent. All right, so this is the mnemonic SOHCAHTOA in case you need to remember it. Now for the next one, cosecant. Cosecant's formula is once again hypotenuse over opposite, and that gives me 10 over 6, or 5/3. Then next is secant theta, which is adjacent over hypotenuse. Oops, I'm sorry, not adjacent over hypotenuse. It's hypotenuse over adjacent. And that gives me 10 over 8, which would then give me 5/4. And cotangent theta is going to give me adjacent over opposite, which would give me 8 over 6, or 4/3. Now, if you haven't realized it yet, the sine, cosine, tangent, the cosecant, secant, and cotangent here are just the reciprocals of the sine, cosine, tangent respectively. So if you look closely here, you'll see, oh yeah, they are reciprocals of each other. So we call cosecant, secant, and cotangent, these 3 right here, these are called the reciprocal trig functions. Now, in right triangle trigonometry, they don't serve much purpose, but when we're identifying or simplifying trigonometric expressions or equations, we tend to use the reciprocal trig functions for these types of problems. But for now, we're just going to keep it simple and just say sine's reciprocal is, cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. In this next example, we're going to do the same thing, but this time we're missing a side right here. So we want to figure out what is the value here. And we know that given to us right now is that 5 is our opposite based on the angle, 13 is the hypotenuse, And whatever this mystery here is adjacent. So when you're given two sides of a right triangle and you're missing a third one, you may remember a formula that we can use here, and I'm pretty sure you do. It is called the Pythagorean Theorem. So in the Pythagorean Theorem, we show a squared plus b squared equals c squared, where a and b are the legs of the right triangle and c is the hypotenuse. So since we're missing a leg here, let's just say that b is what's missing for us, okay? So I'll just call this one here b. So if I plug this into Pythagorean Theorem, it would be 5 squared plus b squared equals 13 squared. Alright, and that gives me 5 squared is 25 plus b squared equals 169, which is 13 squared. Then to solve for b squared, I would move 25 over to the other side and make it negative. So it becomes b squared equals whatever 169 minus 25 is, which is 144. And because it is b squared, I'll solve for b by taking the square root. And that gives me b equals 12. Now, using that 12 here, I know now that b equals 12 is an important number. So now I can actually find all 6 trig ratios here. So sine of theta equals opposite over hypotenuse, so 5 over 13, which then leads me to show that cosecant is equal to 13 over 5, because it is the reciprocal of sine. Cosine of theta is equal to 12 over 13, which shows that secant is equal to 13 over 12. And tangent is equal to 5 over 12. And the reciprocal of tangent is cotangent. 12 over 5. Voila, that's your that's your 6 solutions, but using the reciprocal helped with finding 3 of them much easier than normal. Now our last example, we have a third side missing this time, and that third side would be the hypotenuse. So our mystery value here is a question mark, but we know that that missing side is our hypotenuse. Here's opposite once again, and here's adjacent. Now once again, we'll apply the Pythagorean theorem from the previous slide. So I would get 3 squared plus 5 squared equals c squared, right? Now I get 9 plus 25 equals c squared. And 34 equals c squared, which gives me the square root right here and right here. And c equals the square root of 34. And most of the stuff in trig, we like to keep it in radical form, so don't use a calculator to simplify it. Now, if we do our trig ratios here, sine of theta is opposite over hypotenuse, so it's 3 over root 34. However, here's the dilemma. 3 over root 34 is something we don't like in our fraction because the denominator should not have a radical. So if you're faced with something where there's a radical at the bottom, you do something called rationalizing the denominator as follows. Alright, if you have a radical at the bottom, multiply the top and bottom by that radical. Now, it stands to show that the square root of 34 times the square root of 34 will just cancel each other out. So this becomes 34 at the bottom, and you get 3 square root of 34 over 34. That's one solution. Then the cosine of theta would also then be 5 over root 34. But we want to rationalize the denominator. So do this and then that, multiplying square root of 34 top and bottom would give me 5 square root of 34 over 34. And then tangent of theta would then give me 3 over 5. Nothing fancy here. And then the reciprocals, cosecant of theta equals root 34 over 3. And we don't need to rationalize here because there's no radical at the bottom. And then secant of theta, once again, we're not going to rationalize. Secant of theta is root 34 over 5. And cotangent of theta is 5/3. Alright, voila. Now, hopefully this video helps you understand the 6 trigonometric ratios and how to apply them onto a right triangle. It also gave a good review for those of you that have already taken algebra. It gave you a good review of what rationalizing the denominator was, as well as for those of you that took geometry already, it gave you a good review of the Pythagorean Theorem. So hopefully this video helps. Feel free to leave any comments below, and hope to see you on the next video.